Most people are familiar with the standard story of how the universe began. It starts with a singularity, an infinitely dense, hot point with no size, known as a singularity. This singularity exploded, creating all the space, energy, and matter that make up our universe in an event called the Big Bang. Between 10 to the power of -36 seconds and 10 to the power of -32 seconds after this explosion, the universe expanded at an incredibly fast rate, growing drastically in size. After this period, space continued to expand, though at a much slower pace, and this is the universe we observe today. This is known as the inflationary theory of the early universe, the most widely accepted explanation of how the universe began. However, a few physicists challenge this view. They propose that the universe didn't begin at the Big Bang but has existed forever, expanding both into the past and the future. In this view, the universe was actually contracting before the Big Bang, and what we consider the Big Bang was merely a bounce, when a previously contracting universe reversed course and began expanding. Some theorists even suggest this bouncing could be endless, with cycles of expansion and contraction. This is in stark contrast to the conventional idea held by most cosmologists that everything began with a Big Bang. However, what's important here is that this bounce theory isn't the only one that challenges the Big Bang model. Notably, renowned physicist Brian Cox also questions the Big Bang theory, arguing that something cannot arise from nothing. Adding complexity, the James Webb Space Telescope has made numerous unexpected discoveries that contradict the idea that the Big Bang marked the beginning of the universe. These findings raise an intriguing question. If the Big Bang wasn't the beginning of the universe, then what was it? Could the universe have started with a bounce, or something entirely different? The idea of a universe with a beginning or a day without a yesterday dates back to 1927 when Georges Lemaitre first proposed it. Although many still cling to the idea of a singular starting point for the universe, recent discoveries suggest that the Big Bang is no longer seen as the definitive birth of the cosmos. Instead, it's now understood that the universe's history is far more complex. Today, in 2023, there's compelling evidence suggesting a more intricate origin story. Our universe likely didn't begin with the Big Bang. Rather, it's better described by an inflationary period that preceded it. The Big Bang marks the end of this period of rapid expansion. Let's explore what happened during this inflationary phase. During inflation, the universe was empty. There were no particles, no photons, just the vacuum of space itself. However, this vacuum space contained an immense amount of energy, fluctuating over time by a tiny amount. As the universe inflated rapidly, these fluctuations expanded, creating new small-scale variations that grew into larger structures as inflation continued. This inflationary phase lasted for a brief but significant time before coming to an abrupt end. If you lived in an inflating universe, you might find yourself in a region where inflation stopped, while nearby areas continued to expand. In such regions, you could observe what happens right before a Big Bang as that region recedes from view. In a region of space as small as a hamster ball, yet potentially much larger, the energy within space would be converted into matter and radiation. This transformation is quick, taking only around 10 to the power of -33 seconds. In this short time, energy bound in space would turn into particles, antiparticles, and photons, dramatically increasing the temperature from just above absolute zero to around 20 Kelvin. The universe would be filled with radiation, and everything, whether massive or massless, would be moving at near the speed of light, creating a very different environment from before. This transformation is known as reheating, and it occurs right after inflation ends, when the hot Big Bang phase begins. As the universe cools, regions that were once expanding quickly now slow down, while other areas that remain in the inflationary phase continue to expand. This leads to a noticeable shift in how the universe behaves. Before inflation ends, the universe is growing at an accelerating rate, but after it, regions slow down and the expansion continues, albeit at a more moderate pace. This shift in expansion rates creates two distinct areas, one where inflation stops and one where it continues. These regions, where inflation ends, quickly become filled with matter, antimatter, and radiation, and begin expanding more slowly compared to the regions still under inflation. This process of expansion and transformation forms the universe we see today, where different parts of space expand at different rates, and those areas where inflation ceased grow slower. Thus, while the universe continues to expand, regions where inflation happened in the past will soon retreat from each other, isolated from other parts of the cosmos, which will expand at different rates. In the standard inflationary model, this change in expansion rate means that regions where the Big Bang occurs are disconnected from each other. It's extremely unlikely that two areas where separate Big Bangs happened will ever meet. This model not only helps explain the origins of our universe but suggests that there may be multiple universes, each with different histories of inflation, expansion, and eventual cooling. The interface where we will eventually reside is profoundly fortunate, marking the end of expansion and the transition of the energy intrinsic to space into a hot, dense, and nearly uniform sea of particles. The only irregularities, or departures from uniformity, are the quantum fluctuations that were present and stretched across the universe during its expansion. These quantum fluctuations, corresponding to positive and negative energy, resulted in initially overdense and underdense regions. While we cannot directly observe these fluctuations from that early era, we can infer them by studying the cosmic microwave background (CMB) radiation, which provides a snapshot from 380,000 years after the Big Bang. This allows us to extrapolate back and reconstruct the universe's early density variations, which align with our understanding of cosmic expansion. However, discrepancies between the CMB data and our current cosmological model suggest that something is amiss. The universe isn't behaving as expected on large scales, and light from the CMB is distorted by gravitational lensing, which bends and amplifies light from distant sources. This discrepancy does not match predictions based on our current understanding of cosmology, leading to what has been described as a crisis in the field. Additionally, the temperature differences between the two hemispheres of the CMB sky are puzzling. According to our model, the universe should have started as a uniform entity, but the CMB shows otherwise. Lastly, there are inconsistencies in the value of the Hubble constant, which measures the rate of the universe's expansion, depending on whether we calculate it using the CMB or more localized measurements of distant stars. These anomalies suggest that we may be missing something fundamental in our model of the universe. One possible explanation could be found in loop quantum cosmology, LQC, which arises from loop quantum gravity, LQG. LQC proposes that space itself is quantized, made of discrete particles, or quanta, and that there is a smallest possible size for space, approximately 10 to the power of negative 35 meters. This challenges the traditional Big Bang model, suggesting that the universe did not begin in a singular, infinitely small, dense state, but rather underwent a bounce from a previous universe that contracted and then expanded again. In this view, the universe may have been cyclic, with multiple cycles of expansion and contraction, similar to concepts found in Hindu cosmology. LQC proposes that, in the early universe, space itself would have had extreme curvature. This curvature would be detectable in the CMB as deviations in temperature across the sky. If the universe indeed had positive curvature, this would explain some of the observed irregularities in the CMB, such as the hemispherical anisotropy, where the temperature differs across the two halves of the sky. This explanation resolves what was previously considered a puzzling issue and suggests that quantum gravity at small scales could be responsible for these discrepancies. The larger-scale anomalies, such as those involving the CMB lensing, may also be explained through LQC. According to researchers like Dr. Parampreet Singh, these effects could be due to quantum gravity interactions occurring very early in the universe's history. If these effects are real, they could offer a fascinating new perspective on cosmology. However, the hypothesis that the universe began in a big bounce remains speculative, and substantial evidence is needed to confirm it. One of the challenges we face in understanding these anomalies is the limitation of our observations. It's possible that we are only seeing part of the universe, leading to what is called cosmic variance, which complicates our ability to confirm these findings with certainty. While this remains a significant hurdle, the possibility that these new quantum gravity-driven ideas can simultaneously explain multiple anomalies in the CMB is intriguing and warrants further investigation. Nonetheless, until more concrete evidence emerges, these abnormalities in the CMB remain an open and unresolved mystery in modern cosmology.